Welcome. This is probability, the addition rule. So we're going to solve some problems together as well as learn some more things about probability. A red number cube and a blue number cube are rolled. So we have two separate dice. One is red, one is blue. So you can see all the different combinations. It's easier to see when there's two are different colors. You can see that the red can be 1, 2, 3, 4, 5, and 6, and the blue can be 1, 2, 3, 4, 5, and 6, and we can pair each one of those different numbers with the number from the other cube. So we want to find the probability that the sum is 6. First of all, which of our dice combinations here show a sum of 6? Purple 4.
Five and 1. 4, 2, 3 and 3, 2 and 4, and 1 and 5.
Yep. Those are our outcomes where we have a sum of 6. So probability of 6 equals, right? What would the probability be? Red 5. What would the probability be?
5 out of 36.
You are correct. All right, so let's try the next one. The difference is 6. So we'll erase these. All right, so which ones show a difference of 6? No purple 2. Anyone at the red table? Which ones show a difference of 6? Right. They're 6 apart. Jade is looking confused.
Okay, so there's 2 numbers, right?
Right.
So one of the numbers,
Has to be 6 larger.
6 larger.
Yeah, so that the difference would be 6. Anyone? None of them. So the probability that the difference is 6 is 0. There were none that had difference of 6.
None of them. Because none of them go greater than
Yep. And I'm going to apologize now on this tape that my allergies are like through the roof, and so I will be sniffling and all kinds of other things. So sorry about that. And my eyes will be tearing. All right, so probability that the red cube is greater. Which options show the red cube being greater? Anybody at the yellow table? Now that looks like a 6, doesn't it here? The probability is 6. Yeah. So how about which ones show the red cube being greater?
just for 6?
No. So
Or in general?
in general, the red cube is greater. So which are outcomes that show the red cube being the greater one? You don't have to count them, just tell me which ones. Which one's the circle?
Oh. So 2, 1.
2, 1, there's one.
3, 1, 3, 2. 4, 1, 4, 2, 4, 3.
That's something. And the 4, 1, 5.
5, 2, 6, 2, 6, 3, 5, 3, 5, 4, 6, 4, 6, 5.
Right, so those are all of our outcomes where the red cube had the greater number on it. So what would be the probability that the red cube is greater? No red 4. Yellow 1, no. Green 2. Anyone at the orange table?
15 out of 36.
Is this in lowest terms class? What would that reduce to? 5 twelfths is correct. Yeah, both of those are divisible by 3, so 5 twelfths. Okay, any questions on this one? Let's continue. All right, some vocabulary for you. So the sum of all probabilities in a sample space is 1. So 1 is everything. It's 100%. You have a 100% chance you're going to get something in your sample space. The complement of an event is a set of all outcomes not included in the outcomes of some event. Right? So the complement of an event is a set of outcomes that are not in the event. So the probability of a complement of event, since they have to add up to 1, right? If we take 1 and we subtract the probability of some event, we're going to get the complement of the event. And let me see if I can grab some notes so I can guide you filling in the notes. This one's all filled in, this part. But I want you to add what's at the bottom here. All right, so add this part to your notes. So if E is a favorable outcome, the complement is all the outcomes that are not in E. Sometimes it's easier to find the probability of a complement than it is to find the probability of an event, right? Especially if the event's kind of complicated. So for instance, here we have an example. The probability that the number cubes are all different. Right? So we could take the complement of that is that the probability that the number cubes are all the same. So we could find the probability of the event the number cubes are all different by taking the complement and subtracting from 1. So together, the number cubes are different and the number cubes are the same. That's all the outcomes they can be. They're either different or the same, right? So together they add up to 1. So if I were to subtract the complement from 1, I would get the probability of my event. Right? So the probability of the complement, the probability that the number cubes are the same, that would only be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So there's 6 of those. And there are 36 outcomes with a dice. So the probability of the complement is 6 over 36, or 1/6. So if I subtract 1/6 from 1, we're going to get the probability of the number cubes are all different. Right? So sometimes it's a lot easier to find the probability of your complement, and you can just find that and subtract from 1, and you can find the probability of the event. Any questions on complement? I'm going to do a little bit more with complement, but so you at home are watching this, you can take notes, or wherever you happen to be, robotics. Right, so let's take a look at this problem where we could use the complement. There are 25 students in a study hall. The table shows the number of students who are studying a foreign language. What's the probability that a randomly selected student is not studying a foreign language? Right, so first we should extend our column a little bit. And I think this one is in your notes at the bottom of the page. Let's add one more row here. Right, and let's add the total foreign language. Right, so how many students are studying a foreign language from our table here? 21. So we could use a complement to find the probability of not studying a foreign language. So the probability of not studying a foreign language is going to be equal to 1 minus the probability of studying a foreign language. What's the probability of studying a foreign language in this study hall? Orange 5.
It's 1 minus,
No, what's the probability of foreign?
it's 21 out of 25.
21 out of 25. So if we take 21 out of 25 and subtract it from 1, we'll have the probability of not studying a foreign language, because we have the information for probability of studying a foreign language. We'll just have to change the denominator here so we can combine them. So this would be 25 over 25. Right? Ew, what a horrible looking 25. Whoops. All right, so our probability is going to be 4/25. Right, so sometimes we don't have information on the not or of an event. And so if we don't have information on an event or the event's difficult to find the probability of, we can just find the probability of the complement and subtract from 1. Try not to put it. That doesn't need to be on tape. There we go. I'm fine until I leave the house. And then all the nasty little pawns come attack me. I'm like the people in the commercial where the woman's being chased by the giant flower. So I got this one in your notes, and we can turn the page. All right, so let's look at experimental probability. You can estimate the probability of an event by using data or by experiment. So that's the word that goes in the blanks, I believe. Yeah. For example, if a doctor states that an operation has an 80% probability of success, 80% is an estimate of probability based on similar case histories. So that's not something you would have theoretical probability you'd be able to find on. There's no way to account for everything that can happen during the operation, but they can look at the previous success rate and use that to calculate a probability. Each repetition of an experiment is a trial that goes in the next blank. The sample space of an experiment is the set of all possible outcomes. The experimental probability of an event is the ratio of the number of times that the event occurs, the frequency to the number of trials. So we take how many times it occurs over the number of trials. So this one's in your notes. Experimental probability is the number of times the event occurs versus the number of trials, the number of times you did something. Experimental probability is often used to estimate theoretical probability and to make predictions. So let's do some experimental probability. The table shows the results of a spinner experiment. Find the experimental probability. Let's add to this, and this one's in your notes. Let's add to one more row to this table. And let's add total trials. So how many total trials were there? 50. So what's the probability of spinning a 4 based on our experimental data? Anybody at the purple table? So the probability for experimental. It's going to be number of times something occurs, or frequency, divided by number of trials. So what would that be for probability of spinning a 4? Purple table? I don't want a percent. I want a fraction. Yep. We're going to keep these as fractions, right? Unless your data is given to you as a percent or a decimal.
Can we reduce it?
And we should reduce. What would that reduce to?
7/26?
Yep, 7 over 25. How about spinning a number greater than 2? All right, so how would we calculate that out? Orange 2. Oops. Did I go so far?
Does that include 2 or exclude?
Excluding 2, because it's greater than 2.
So it would be 11 over
Oops. So I need to plug in.
11 over 2.
No, that would be the probability. That would be probability for a 2.
There it is. It's, it says greater than. There we go.
All right, now we're all charged up. That would be the probability of 2. We want probability of greater than 2.
So, 14 and 19.
Yep. Yep, we'd have to combine those two. So it would be the probability of spinning a 3 plus the probability of spinning a 4, which would give us 19 over 50 plus 14 over 50, which would be 33 over 50.
If you reduce it, it's 2/5.
No, that doesn't reduce.
But it was 10.
Yeah, if it was 30 for 50, it would, but. Right, so we would add those two. And this one's in your notes, so just fill out your notes. Very good. Right, there's more experimental probability. The table shows the result of choosing one card from a deck of cards, recording the suit, and then replacing the card. What were the number of trials? Right, we'll just add those together. We want the probability of choosing a diamond. What would that be? Yellow 3. Yep. All right, how about the next one? The experimental probability of choosing a card that is not a club. So probability, by the way, I didn't mention this in the other class, but that little symbol there means not. So I'm just going to put the little symbol there. So not club. Oops. So this here means not. Just put a little squiggle there. All right, so not a club. Let's use the complement. All right, so to use the complement, we're going to take 1 minus the probability that we get a club. What's the probability of getting a club? Purple 3.
726.
726. So our probability would be 2626 minus 726, which would give us 1926. Right, so one way we can find the probability is to just subtract off what we don't want. We don't want club. And that gives us everything we do want.
Okay. I'll be right back.
But you got this one in the notes? It's not going to be my best recording. That's a nose blowing. Right, union and intersection. Right, so this is for your note. This is in your notes, and I'm going to just have you add what's written in blue there. So the union of A and B are elementary events that belong to either A or B or both. It's written as the union, so it's that U symbol. It looks like a U. If we turn the U upside down, we have intersection. So the intersection of A and B are elementary events that belong to both A and B. And I want you to add to your notes what they have in common. Moving along. So in your notes, a simple event is an event that describes a single outcome. Okay, so that you can fill that part in your notes. So simple event is something like rolling a 4. A compound event is made up of 2 or more simple events. rolling a 4, and a 6. Mutually exclusive events are events that cannot both occur in the same trial of an experiment. Rolling a 1 and rolling a 2 on the same roll of a die are mutually exclusive. You can't roll a 1 and a 2. Right? So mutually exclusive events have no sample spaces in common. There's nothing in the intersection. And you have this in your notes on the next page. I want you to add the following things to your notes. So U is union. It means all the outcomes together. And then the upside down U is intersection. It has to be in both groups. And then if our two groups are mutually exclusive, we say their intersection is this symbol here, which means empty set or null set. Right? So it's not a 0. It means there's nothing, because a 0 would be an element. Right? This is nothing, absolutely nothing in the intersection. Right? So it's empty set or null set. They have no elements in common. So just add the things that I have written in my handwriting there, the additional notes. Oops. In first period, we got to the very top of the 4th page. I think we will here too. And I think I'm going to end this podcast here and just start the next podcast, so it's not too long. So bye for now, and we'll come right back in the same class period.